law of thermodynamics. So let us first define what is thermodynamics. So it is the science that treats the transformation of heat energy into mechanical energy and the reverse process, the conversion of work into heat. It is not only the energy that is conserved, but there's also limits on this efficiency, as we will see later on, specifically on engines and refrigeration. So, when the law of energy conservation is broadened to include heat, we call it the first law of thermodynamics. It states that the net heat absorbed by a system is equal to the sum of the net work done by the system and the change in the internal energy of the system. So, the first law of thermodynamics is an overall principle that is not concerned with the inner workings of the system itself. Whatever the details of its molecular behavior in the system, the added heat either increases the internal energy of a system or enables the system to do external work, or both. But how do we assign sign conventions, or how do we follow sign conventions in problems involving thermodynamics? So remember this, heat is positive if it is put into a system, and negative if it was expelled. On the other hand, work done by a system is positive and work done on a system is negative. An increase of internal energy is positive and negative if it decreases. So remember that. So for thermodynamic processes, so we have four specific kinds which occur in practical situations. So first is the isobaric process. An isobaric process is a constant pressure process. So yun yung lagi natin tatandaan. It is a process at constant pressure. So in general, none of the three quantities, the delta U, Q, and W is zero in an isobaric process. Therefore, the formula or the equation for isobaric process is delta W is equals to P delta V or PV. So, what are the examples of an isobaric process? So, usual examples include boiling water at a constant pressure and other techniques of cooking. So, when we draw a PV diagram for isobaric processes, the work done by the system is equal to the area underneath the curve on a PV diagram. So, throttling processes occur when a fluid at high pressure seeps adiabatically through a porous wall or narrow opening into a region of low pressure, which brings us to the next type of thermodynamic process. An adiabatic process is defined as one with no heat transfer in or out of the system. Therefore, in this adiabatic process, your Q is equals to 0. We can prevent heat flow either by surrounding the system with thermal insulators or thermally insulating materials, or by carrying out the process so quickly that there is not enough time for appreciable heat flow. This process is represented by the equation delta W is equals to negative delta U. The compression stroke in an internal combustion engine is an approximately adiabatic process. An isochoric process is a constant volume process. So, yun naman lagi natin tatandaan. Constant volume process. So, when the volume of a thermodynamic system is constant, it does no work in its surroundings. So, no work is done. Therefore, your W here is 0. And therefore, your resulting equation is delta Q is equals to delta U. So, in an isochoric process, all the energy added as heat remains in the system as an increase in internal energy. Heating a gas in a closed, constant volume container is an example of an isochoric process. And lastly, an isothermal process is a constant temperature process. For a process to be isothermal, any heat flow into or out of the system must occur slowly enough that thermal equilibrium is maintained. So in general, none of the quantities in an equation, none of the quantities delta U is 0 in an isothermal process. Therefore, the formula for for our isothermal process is delta Q is equals to delta W. So the most familiar system having this property is an ideal gas. So here are the diagrams for the four thermodynamic processes discussed previously. So here are the three main types of thermodynamic systems naman. So in an open system, there are both mass and heat transfer. In a closed system, only heat transfer occurs. And if we talk about, or if we say isolated system, nothing occurs. So there is no heat transfer nor mass transfer. So let's now talk about the second law of thermodynamics. So suppose you place a hot brick next to a cold brick in a thermally insulated region. You know that the hot brick will cool as it gives heat to the cold brick, which will warm. The two bricks will arrive at a common temperature, thermal equilibrium. No energy will be lost, which is in accordance with the first law of thermodynamics. But suppose that the hot brick extracts heat from the cold brick and becomes hotter. Would this violate the first law of thermodynamics? No, if the cold brick becomes colder so that the combined energy of both bricks remain the same. However, if this hypothetical scenario is likely to occur, this would violate the second law of thermodynamics. The second law of thermodynamics identifies the direction of energy transformation in natural processes. This law states that it is impossible to construct an engine which operates continuously, produces no effect other than the extraction of heat from a reservoir and the performance of an equivalent amount of work. Or simply, heat of itself never flows from a cold object to a hot object. So the development of a general statement for the second law of thermodynamics was based in part on the study of heat engines. A heat engine is any device that uses heat as input and provides mechanical work as output. The basic idea is that a heat engine, either a steam engine, internal combustion engine, or jet engine, is that mechanical work can be obtained only when heat flows from a high temperature to a low temperature. Usually, a quantity of matter inside the engine undergoes inflow and outflow of heat, expansion and compression, and sometimes change of pace. So we call this matter the working substance of the engine. In a heat engine, regardless of its working substance, it obeys the following processes. So number 1, a quantity of heat is supplied to the engine from a reservoir at a high temperature. Second, mechanical work is done by the engine through the use of a portion of the heat input. And the third, or lastly, a quantity of heat is released to a reservoir at a low temperature, which is usually called a sink. So the purpose of any engine is to transform as much of the extracted energy into work as possible. We measure its success in doing so by its thermal efficiency, or the efficiency of a heat engine, which is defined as the work the engine does per cycle, or the energy we get, divided by the energy it absorbs as heat per cycle, or the energy that we pay for. So it can also be defined as the ratio of the useful work done by the engine to the heat put into the engine, and it is usually expressed as a percentage with the formula below. A Carnot engine is an ideal engine. In principle, it has the maximum possible efficiency for an engine that absorbs heat from a high-temperature reservoir, performs external work, and deposits heat to a low-temperature reservoir. However, engines that undergo Carnot cycle are non-existent because efficiency of 100% can only be attained when reversible processes are used. However, in real life, irreversible processes such as friction and turbulence occur, which hinders the acquisition of a 100% heat engine efficiency. An ideal engine has the highest possible efficiency for the temperature limits within which it operates. The efficiency of a Carnot engine is given by the formula below. So E equals T sub I minus T sub O divided by T sub I. The gasoline engine, used in automobiles and many other types of machinery, is a familiar example of a heat engine called internal combustion engine. This term, the term internal combustion engine, usually refers to an engine in which combustion is intermittent and generates the input heat within the engine itself, such as the more familiar 4-stroke and 2-stroke piston engines. The first modern internal combustion engine was created in 1876 by Nicolaus Otto. On the other hand, the diesel cycle is similar in operation to the gasoline engine. The most important difference is that there is no fuel in the cylinder at the beginning of the compression stroke. A little before the beginning of the power stroke, the injectors start to inject fuel directly into the cylinder, which is fast enough to keep the pressure approximately constant during the first part of the power stroke. Because of the high temperatures developed during the adiabatic compression, the fuel ignites spontaneously as it is injected. Therefore, no spark plugs are needed. That same Nicolas Otto presented his version of Carnot engines, but for gasoline-powered engines. This became known as the Otto engine that operates under the Otto cycle. A gasoline engine operating on the Otto cycle has a theoretical maximum thermal efficiency of E that depends on the compression ratio R and the ratio of heat capacities gamma of the working substance. A refrigerator is a heat engine operating in reverse. So in heat engine, it takes heat from a hot place and gives off heat to a colder place. A refrigerator does the opposite. It takes heat from a colder place and gives it off to a warmer place. So a heat engine has a net output of mechanical work. The refrigerator requires a net input of mechanical work. In an ideal refrigerator, all processes again are reversible, and no wasteful energy transfers occur as a result of friction and turbulence. A perfect refrigerator, one in which no work is required to take heat from the low temperature region to the high temperature region, is not possible. This is the Clausius statement of the second law of thermodynamics. No device is possible whose sole effect is to transfer heat from one system at a temperature into a second system at a higher temperature. The coefficient of performance, or COP, of a refrigerator is defined as the heat removed from the low temperature area, which is the inside of a refrigerator, divided by the work W done to remove the heat, as shown below. A refrigeration system is made up of several parts. So number one is the refrigerant, which is a fluid that is liquefied easily by an increase in temperature or a drop in temperature. Next is the compressor, which provides necessary input of work to move the refrigerant to the system. Next, we have the condenser, which is the part that the refrigerant may be cooled by running water or by an electric fan. Next, we have the throttling valve, in which the refrigerant liquid at high pressure drops to the lower pressure required at the evaporator and is directed to the evaporator. And lastly, it is indeed the evaporator, which provides the cooling inside the refrigerator, which moves heat out of the system.
Suppose 200 joules of work is done on a system and 70 calories is extracted from the system as heat. In the sense of the first law of thermodynamics, what are the values including algebraic signs of W, Q, and U? So W is the work, Q is the heat, and U is the internal energy. So for the work, we are given here 200 joules of work that is done on a system, so that is negative. So if the work is done by the system, it should be a positive. Next, for heat, that is negative 70 calories since it is extracted from the system. And we convert this into joules. So 1 calorie is 4.184 joules, and that is equal to negative 293 joules. For the internal energy, that is Q minus work. So that is negative 293 joules minus minus, so that's plus. Plus 200 joules equals negative 93 joules. The Carnot engine has an efficiency of 22%. It operates between constant temperature reservoirs, differing in temperature by 75 degrees Celsius. What is the temperature of the lower temperature and higher temperature reservoir? So we are given an efficiency of 22%, so we convert it into decimal place, that is 0.22. And the formula for an efficiency of a Carnot engine is equal to efficiency equals 1 minus low temperature over high temperature reservoir. So for the change in temperature, we are given high minus low. So our TH minus TL is equal to 75 degrees Celsius. So it happens here that it is in Kelvin because you can also convert the change in temperature. Let's say we have a temperature here of 275 degrees Celsius and the low temperature is 200 degrees Celsius. So if you convert this into Kelvin, you add 273. And if you subtract, that 273 will cancel and 275 minus 200 is still 75 Kelvin. So the high temperature is equal to 341 Kelvin, and if you convert that, you deduct 273 equals 68 degrees Celsius. For the low temperature, you just again derive the formula. So that is delta T, that is TH minus TL, and you are looking for the low temperature, so that is the difference between the high temperature and the change in temperature. So that is 341 minus 75 equals 266 Kelvin, and you convert it, that will equal to negative 7 degrees Celsius. A Carnot air conditioner takes energy from the thermal energy of a room at 70 degrees Fahrenheit and transfers it as heat to the outdoors, which is at 96 degrees Fahrenheit. For each joule of electric energy required to operate the air conditioner, how many joules are removed from the room? So for this problem, you will use the coefficient of performance under refrigeration, since air conditioner is a reverse process of the law of thermodynamics. So the coefficient of performance K is equal to the low temperature over the high temperature minus the low temperature. So we have a low temperature of 70 degrees Fahrenheit and a high temperature of 96 degrees Fahrenheit. You convert them into Kelvin, that's equal to 294 Kelvin for 70 degrees Fahrenheit and 309 Kelvin for 96 degrees Fahrenheit. So you solve, that is equal to 19.6, and it is unitless. But we are looking for the energy required. So again, we use the other formula, that is QL over work. And we are looking for the energy that is QL because it's removed, so that's low. If it is as what is added, you find the W or the work. So you are given Q equals KW, that is the coefficient of performance, multiply 1 joule. Since we are looking for each joule, so we just need 1. So that is equal to 19.6 joules.
Thank you for listening. I hope you learned something today and see you on the next discussion video.